Hi, my name is EBERHARD, and I'm going to be presenting to you about the wave-particle duality of photons. Before we begin, let us think back to the old adage where several blind people are touching an elephant and describing what they are feeling. As you can see from this comic, each one describes something different and thinks that the elephant is something different than it actually is. This is applicable to our discussion because photons can be observed as either particles or as waves. Scientists throughout the centuries have done experiments on light to observe its properties. Many of these properties have been similar to those that waves exhibit. Other properties have been more similar to those that particles exhibit. While observations supporting both theories are correct, neither describes the whole picture on its own, as photons are a combination of both of these. To begin, we're going to talk about the particle-like properties of photons. The first being that photons exhibit momentum. We see this, for example, in comets. As they orbit the sun, their tails always face directly away from the sun. This is because as dust particles are hit by these photons, they continue in the same directions that the photons were originally traveling. Photons are also individualized quanta. They are massless, but instead of being a continuous stream as a pure wave would be, they actually have individual concentrated points of energy. The last particle-like property that we're going to discuss is the collisions and interactions that it has with other quantum particles such as electrons and protons. This is going to be similar to other particles that we see in our lives, such as rocks or books or balls, etc. Watching this animation as a photon hits an electron, it becomes excited and moves to a different orbital. This shows the particle-like properties that photons have. We will continue by talking about the wave-like properties of photons. These include, but are not limited to, interference, diffraction, wavelength, and frequency. We will not go into depth about many of these things, but it will suffice us to say that wavelength, frequency, energy, etc. have all been observed by scientists throughout the years in photons. One of these experiments was conducted by Dr. Thomas Young, a British scientist in the 19th century. He famously conducted what is now known as the slit experiment. In this experiment, he passed light through a material impermeable to light, leaving a single slit open. If photons were simply particles, all we would see on the wall opposite the light, after passing through the slit, would be a pattern very similar to the slit in shape and in size. However, in reality, we saw a pattern that was much wider than the slit. This shows that the light was diffracted as it passed through the slit, as we would expect a wave to behave. Next, two slits were placed side by side in parallel fashion. The lower image on the right shows what appeared on the wall. This animation shows this experiment in action. As you can see, as the light emanates from the two slits, the waves interact before contacting the wall. At some points along the wall, the waves are constructive and build upon each other. At other points, they are destructive. The action of these waves shows what is actually happening. Here, as we see, the blue wave and the red wave are interfering with each other in a destructive manner, meaning when they hit the wall, their waves will cancel each other out and we will not see any light. At points, this interference is constructive, and as the two waves come together, their troughs and their valleys match up, and they are constructive, giving a brighter intensity to the light. With this understanding, let us watch this animation one more time. As we see in the very center, as the constructive waves give a very intense point on the wall. After this duality was discovered, another scientist named de Broglie theorized that everything that we see, all matter, actually shows wave-like properties. It is simply the fact that their wavelengths are so small and that the objects they interact with are so large that the effects are negligible. Although this is difficult to prove, many scientists, including Albert Einstein, agree with him. In conclusion, we have seen that photons exhibit both wave and particle-like properties. Many experiments have been conducted observing these apparent properties. While it's difficult for us to completely understand this duality because the objects around us exhibit either wave-like or particle-like properties. This duality exists will help us to greater comprehend quantum physics. Finally, I would like to include a few citations where I found the videos and information in this presentation.